So, welcome to our second talk of the day. This talk is given by Kevin Sheldrake. He's a security researcher for many, many years in the industry. And he's talking about cracking HiTag2 crypto, weaponizing academic attacks for breaking and entering. Give a warm welcome to Kev.
Hello, thank you for coming to my talk. I appreciate crypto in the morning is, especially after last night, might not be the easiest thing, but apart from XOR, there's not a lot of maths actually in the talk. The longer version, which you can find on YouTube, has got a lot of more maths in it. The reason I'm talking about HiTag2 will become apparent, but just to give you an outline of kind of the way the talk's going, there are a number of different attacks on the HiTag2 crypto system, and so what I'm going to do in this talk is talk through how the crypto system works and talk through one of those attacks in some kind of detail. If you're interested in the other attacks, I'll point you towards resources online towards the end and other papers that you can look at with the other details in. But I think that it's a very, very, very broken crypto system. I mean, there's at least 6 different ways of attacking it. Understanding what's wrong with this and the way the academics went about breaking it with one particular attack gives you some idea of how you might then attack other crypto systems and how you might spot some crypto systems that are going to be fundamentally flawed before you even start. So that's the idea for the talk. I do work in cyber, and I'm currently a researcher at a company, an international company, but based in the UK. I work from home. I do a lot of radio and crypto, and I did IoT for a number of years, hacking into routers, cameras, mobile phones, baby monitors, child trackers, you name it. If it's small and it plugs in and it runs MIPS or ARM, I've probably had a go at it. So the question, why would we copy or attempt to copy 125 kilohertz RFID tag? So I have an RFID tag here. It's in ISO card format. Obviously, if you have a car key, then that would be in a different format with a different size coil. But these are the ones you'd see in building access control. So people might have this on a badge around their neck and then use it to open a door. The reason why we want to copy these kind of tags is because they're used to protect things of far greater value than the amount of effort it takes to copy them or break the system. Generally, they have no crypto at 125 kilohertz, but HiTag2 is specific in this case where it does have crypto. It's just not very good crypto. I won't be talking about cars, by the way. That's ever so slightly different physical characteristics and a slightly different cipher specification. A normal simple 125 kilohertz RFID tag, you probably already know this, has one kind of page of data. It might be divided into multiple pages, but notionally it's one page of data. And when it's powered by a reader, it transmits that single page of data over and over and over again. And embedded into that page of data is a synchronization pattern. The reader spots that synchronization pattern in the continual stream of numbers coming its way and synchronizes on that, and whatever comes after it takes that to be the unique identifier, and that's the number it then uses to decide to open doors or not. Physically, you've got a situation kind of like this. So the reader emanates a field, the tag has no battery, 125 kilohertz or at 13.56 megs. I'm only going to deal with 125 kilohertz. But it's powered by the field, so it absorbs energy from the field. It then transmits information to the reader by modulating that field, but essentially damping its coil by closing the circuit or not on the coil. And the reader can detect that change in the field. If the reader wants to communicate to the tag, for example, to issue commands or to write to it, it can turn that field on and off rapidly using pulse width modulation. And the reader, the tag, will remain powered because it has a capacitor inside it to retain the power, and it will notice that field going on and off and receive that binary data. So if you get into RFID, there's a number of different modulation types and encodings that you need to care about, and the more, you only have to be sort of half an hour into your RFID journey and you'll know what all of these mean. I'm not going to go into these in any details. If we want to secure 125 kilohertz RFID, we would expect authentication and encryption, and we'd expect that to be randomized so that you can't replay it and so that it's difficult to copy these tags. So today I'm going to talk very briefly about HiTag2 password mode because it's terrible, and you'll see why in a second. And then I'm going to spend the rest of the time talking about HiTag2 crypto mode, including the random number generator, the stream cipher, and how that's used, and specifically the first attack from the paper, gone in 360 seconds by Verdult, Garcia, and Balash. I didn't invent any of these attacks. All I've done is taken their maths and turned it into tools because they didn't release tools. And 5 years after their paper came out, no one had offered or no one had provided the tools to the White Hat open source community. So I went ahead and wrote those tools. We had a task at work involving breaking into buildings that happened to use these tags as their access control tokens. So we needed the software. No one else had it, so we wrote our own. Well, I did. So there's a number of things I won't be talking about because I don't have time. So I won't be talking about the different modes that HiTag2 can be in beyond crypto mode. They can be specific to a particular system, and there's a whole load of complications that come with that you would probably want to know about if you're dealing with it. I won't be talking about cars because car keys are HiTag2 for the deimmobilization up to 2016. After 2016, they'll probably have a different cipher, a different crypto system. Some cars use the HiTag2 cipher over 433 megahertz for remote keyless entry. Again, typically up to 2016, where they kind of stopped doing that. Other cars use different ciphers. There's for the car keys, there's a number of different ciphers. So, and there's physical differences, and over the 433 megahertz RKE stuff, it's a slightly different protocol. So I'm not going to go into the car stuff because that would be a talk in itself, and I haven't really done a great deal of work there. All my work has been about taking people's badges and using them to break into places. I won't talk about the other attacks from the early papers or the GPU accelerated brute forcing in any detail, but I might demonstrate attack 4 if I get a chance before the end of the talk. So this all started with an academic paper, gone in 360 seconds, and as you can see, hopefully, it's quite a lot of maths and it's quite hard to understand. They don't tend to repeat themselves, so if you don't get it the first time around, you have to kind of just keep rereading the same paragraph until it makes sense. One of the attacks took 3 weeks to try and understand, just in terms of what they were actually saying they were doing, because the equation didn't make any sense to me. Eventually it did. It's not that trivial, which is why I've implemented the tools and I'm making them available, because running the tools is dead easy. So we'll start by talking about HiTag2. If you want to know what's inside one of these, it's kind of this. If you dissolve one in acetone, it only takes a few minutes. You can extract the chip with a 30-pound microscope that you've borrowed from a child and an SLR camera. You can take some photographs, and you might be able to see, probably not from the distance you're at, but it says HT2 on the chip there, which means that you know it's HiTag2. Sometimes that's the easiest way of knowing what kind of RFID you're dealing with. Since doing this, my colleague who did this bit of work has actually built a CNC table with a much more powerful microscope that cost him £10,000 and a really powerful SLR camera, and he can now make enormous detailed images of decapped chips, which is great fun and really hard to get hold of the chemicals for, but that's slightly different. From a logical perspective, HiTag2 looks like this. There's 8 pages. The first page is the unique identifier of the tag, which is factory programmed and read-only, typically. There are allegedly Chinese cards where you can change that, but almost every HiTag2 card you come across, the UID will be read-only. Following that, 3 pages of secrets, password if it's in password mode, key if it's in crypto mode, and a tag password and config byte, which specifies authentication password in the other direction and what mode it's in, and 4 pages of user data. Typically, the information that's used to make the access control decisions is stored in that 4 pages of user data. The UID is only used as a randomization nonce within the authentication. Whether it's in crypto mode or password mode, the entire system shares secrets. I mean, there's not enough power on these things, and they were invented too long ago to have PKI. So they kind of only have to have shared secrets. That's the only really way you could do it, some kind of symmetric secret. And because you might have, like, say, thousands of door readers and tens of thousands or hundreds of thousands of tags in a system, and every tag needs to be able to talk to every door, whether or not it lets them in or not, then each tag and each door has to have the same secret, typically, which means that you can break one part of the system, gain that secret, and then use that secret in every other part of the system. So you can steal one tag from one employee or borrow one tag when they're in the pub and get the secret from it, and then use that to attack the readers, to clone other people's tags, or whatever you like. So it's already weak from that perspective, but it gets worse. Password mode, which you occasionally see, but is really not recommended, everything is passed in clear. So when the tag approaches the reader, the tag sends its UID, the reader responds with the password from the reader to the tag in clear, the tag responds with the password to the reader in clear again, and then they communicate in clear from there onwards. So if you could eavesdrop on that, which you could do with one of these devices that I'll show later if you were close enough and you just wanted to steal the passwords off your own tag, or if you put some metallized tape around the reader to convert the close coupling into some kind of radio frequency, maybe from a few meters away with a decent antenna, you could pick up the secrets, and then the whole system is broken. So we won't talk about password mode any further. Crypto mode looks very similar, except instead of sending the password, the reader sends an encrypted nonce and an encrypted challenge response value to the tag. The tag uses that to authenticate the reader and sends back its encrypted password from the tag, and the reader uses that to authenticate the tag. At this point, they can then communicate using encrypted comms. So if you eavesdrop on it, you shouldn't be able to see the passwords, you shouldn't be able to steal the data, etc. Pictorially, it kind of looks like this. So the reader and the tag both have a key. The tag sends the UID to the reader. The reader invents a nonce. It uses the nonce, the UID, and the key to seed its random number generator and transmits the nonce encrypted over to the tag. The tag uses the same pieces of information to initialize its random number generator. And both the random number generators are then initialized to the exact same point. So they'll both produce the same key stream. So they can now be used in a stream cipher configuration where one end wants to send data to the other end. It can extract the same number of bits from its random number generator as it wants to send, XOR the two together to encrypt in a standard stream cipher kind of way. That gets transmitted to the other end. That end can then extract the same number of bits from its random number generator, which will be the same key stream, XOR that with the received data, and that will decrypt it back to the plain text. So obviously we're using XOR, and it looks a bit like this. But it's the basis of a standard kind of stream cipher. So we'll talk about that random number generator and how it's used. It's based on a 48-bit linear feedback shift register, which are really popular, or were really popular in the sort of 70s to the 90s. NASA used them extensively. You find them in all sorts of places where you shouldn't. They don't make for very good crypto random number generators, unfortunately. So I've got a cable in the way. I'll keep standing on it. There we go. That's slightly better. So it's initially seeded with the UID, which the tag has, and the tag is sent to the reader in clear, and the lower 16 bits of the key. At that point, the reader generates a new nonce, NR. It XORs that with the upper 32 bits of the key, and it pushes that in one bit at a time. As it pushes it in, it extracts PRNG output. It uses that PRNG output to encrypt the nonce. So from here onwards, you'll see red means it's a secret, and green means it's sent in public. If it's got squiggly brackets around it, it means it's encrypted. So NR is the unencrypted secret nonce. NR with squiggly brackets around it is the encrypted version of that nonce, which you can then send in public. Excuse me. The tag has initialized its PRNG to the same point originally. As it receives the encrypted nonce, it decrypts it and pushes it into its PRNG at the same time. So it gets its first bit of output from the PRNG, XORs that with the first bit of the remainder of the key, and XORs that with the first bit of the encrypted nonce, which simultaneously decrypts that first bit of the encrypted nonce and XORs it with the next bit of the key, which is the next bit it has to push into LFSR in order to generate the next state, at which point it can then get the next bit of output and repeat that process. So one bit at a time, it decrypts the nonce and randomizes its PRNG to the same point that the reader is at. I think that's really clever. It's not secure, but it is really clever, because it's kind of decrypting and randomizing at the same time. And afterwards, the reader and the tag both end up in exactly the same situation. If that doesn't make entire sense, read any of the papers on HiTag2, which will explain that process, and you'll be able to work it through in your mind. You'll be able to see how that works. But the important bit is they both end up with exactly the same state inside their PRNG LFSR. So they're going to generate the same key stream. A point that I will labour a lot, because the attack depends on that key stream being repeatable. After it's been randomized, both the tag and the reader then enable the feedback function L, which is publicly known, and it uses that to generate the new bits that get pushed in as you extract bits out of the LFSR. So when you want to encrypt data, you take bits from the LFSR, XOR it with the plain text, and that will give you encrypted. And equally, to decrypt data you've received, you get the bits out of the PRMG, XOR that with the encrypted data, and that will get you back to the data again. It is, as I say, a stream cipher. The feedback function is simply tapping the LFSR at 16 points and XORing all those bits together. The idea being that if you don't know every one of these 16 bits, you can't predict the output, because each of these could be 0 or 1, and the one you don't know could be 0 or 1 will either flip or not the output, or the new value, the output of L. So if you don't know all those 16 taps, you can't know what the new bit will be that gets pushed in. So if you don't know the entire state, it's very hard to know what the next state would be, which makes it look relatively secure. The output of the PRNG is not the bits that fall off the end as it gets pushed and clocked through. It's actually the output of a filter function f, which runs on the state. And filter function f is made up of 3 functions, functions a, b, and c. Each of functions a and b take 4 bits each from the state, so 20 bits in total. Each of those functions produces 1 bit of output, which is fed into function c, which produces 1 bit of output. Each of those functions a and b and c are biased 50-50. So given all the possible inputs for any one of those functions, you'll have 50% of the time you'll get a 1 and 50% of the time you'll get a 0 out. So if you don't know all of those 20 taps, it's very hard to predict whether you're going to get a 0 or a 1 as the output. And equally, once it gets clocked by 1 more bit, again, you're in the same situation. If you don't know those 20 bits, it's going to be hard to know. So going back to that slide on the crypto mode, the tag sends the UID, the reader sends the encrypted nonce, and the encrypted challenge response value, which is essentially FFFF encrypted using the stream cipher, which the tag can then decrypt because it's randomized its LFSR to the same point that the reader was at. That's how the tag can convince itself that the reader is valid. Because if it has a different key, it won't be able to get to a state where it can encrypt that challenge response value correctly. The tag responds with the page 3 value encrypted, which is the tag password and the configuration byte, and that's how the reader can then decrypt that and know that it's definitely the tag is part of the same system. At which point, the reader can send encrypted commands and the tag can respond with encrypted replies. So, let's talk about commands. There are 4 commands in HiTag2, determined by the first 2 bits, CM0 and CM1, read page and read page inverted, which will read pages from the tag. The inverted one means give me back all the bits inverted, right? There's a write page command for changing the values on the tag, and there's a halt command. The halt command is there so that if you have multiple tags in the same field, which I'm led to believe that casinos in Las Vegas have these tags inside their gambling chips, and the entire table is a RFID reader, and they read all of the tags. So the way they read them is that when they send out the start auth command, the tag that is the quickest or the loudest is the one that gets to respond first, and the reader initializes its PRNG based on that tag's UID. From where onwards, only that tag can decrypt the information that's coming. So all the other tags will ignore what's going on. When it's finished talking to that tag, it sends the halt command, and that tag will power down and won't respond again until it's been removed from the field and reinserted into the field. So you can systematically work through all of the tags within the field because the quickest or the loudest is the one that ends up being responded to, at which point you turn it off and then talk to the next one, turn it off, talk to the next one, turn it off. So that's what the halt command is for. Commands, the bits A2, A3 and A4 specify which page you're reading or writing, and in the halt command it doesn't really matter what they are. So a command is 5 bits long, but in the actual protocol they're always 10 bits or more, because for integrity they take the command and follow it with the bit inverted version of the command, which say that's encrypted and sent to the tag can decrypt that and check if the first 5 bits is the inverse of the next 5 bits. Simply XOR them together and see if you get 0. Or see if you get all ones, sorry. But for extra integrity, you can repeat that as many times as you like, as long as each block is the inverse of the previous block. And you can have thousands of these blocks, as we'll see in some of the attacks, because we'll abuse this badly. So if we talk about attacks, there was a paper from 2012, gone in 360 seconds, hijacking with HiTag2 by Vidal, Garcia and Balash. I've met Flavio Garcia, he's a lovely man, and very, very clever. And I've communicated with Vidal's team since. There was 3 attacks in that paper, they all completely broke HiTag2. At which point it was no use to anyone, it should never be used again. But they didn't release their tools that implemented these attacks, hence the work I did. When I met Flavio, he then pointed out that he'd since produced another paper in 2016 with a 4th attack, which was much faster and required less data, and didn't release the tools for that, so I've since implemented that one as well. Back in 2012, Vincent Imler produced a GPU brute force, which took a long time on a single host with a single GPU, but it did crack using only 2 nonce and challenge response pairs. And in 2017, a French team, 1 car, 2 frames, they took that particular implementation and distributed it across multiple GPUs on multiple hosts in order to speed everything up. And then last year, Verdalt and a new team produced HiTag2 Hell, where they referred to the 2017 brute force as blind and naive, and produced a 500 times more optimized version of the attack, which is an amazing paper. And they did release their tools. They're not entirely finished. You still have to provide a little bit of work, but the vast bulk of the work that you need is there in those. And it's on GitHub. They've got Python, what they call pseudocode, which is Python. And then there's an x86 implementation that will run on a CPU. And there is a GPU kernel that will run on anything with compute 5 or above. So an Amazon P3 instance, for example, will have a suitable graphics card, or GTX 1080 will do the job. So we'll talk about the first attack, nonce replay and length extension. So what you will have noticed is that for a specific tag against the system, the tag's UID isn't going to change if you repeatedly appear with that tag. The key for the system isn't going to change because that's fixed for the long term of the system. The only thing that changes per session is the nonce that the reader generates. The tag generates no entropy whatsoever, which we're going to abuse. The reader sends an encrypted nonce and challenge response value to the tag, and we can eavesdrop on that communication and capture those. We can then pretend to be a reader and talk to the tag, and each time the tag sends us its UID, we can send that same encrypted nonce and challenge response value that we've captured. And that will initialize the tag to the same location in its PRNG each time, so it'll always produce the same key stream for each of those sessions, which is kind of important. So if you remember, after initialization, both the tag and the reader were in this state. As you can see, it's only the key and the nonce that's actually setting that any different to any other tag. So we can create an emulated reader, we can send start off, the tag will respond with the UID, we replay the encrypted nonce, we replay the encrypted challenge response value, the tag will respond with its encrypted page 3, that we can't decrypt at this point, but it doesn't actually matter. It just means that the key stream produced by the tag is solely dependent on that encrypted nonce, which we're going to send the same one each time we talk to the tag. So if we had an encrypted nonce of 4A85B2DF, we might get the PRNG output of 010, 111, 000, 1110, 10, etc., etc. Every time we initialize that tag, we'll get that same key stream. So what should be a one-time pad is now becoming a multi-use pad, which we all know is completely flawed. So the way we're going to attack it is we're going to start out by finding the read page 0 command, the encrypted version of the read page 0 command. And the reason for that is because we know the answer. We know what page 0 is because it's the UID, which gets presented in clear at the beginning of the transaction. Now, the read page commands are 10 bits long, 5 bits followed by 5 bits inverted, and then encrypted. And so therefore, you've essentially got a randomized 10-bit string. So there's 1,024 possibilities, of which 16 will be valid read commands. And if you initialize the tag through that initialization process and send a 10-bit command, the tag will try to decrypt it, and then we'll check the integrity of that command. If it passes the integrity check, it will give you the response as an encrypted response, which will be the 32 bits of that page encrypted with the stream cipher. But if it fails, if the integrity, it will give you the unencrypted error response, F402A89C. And the reason it's unencrypted is because something, as far as the tag is concerned, or as far as the system designers are concerned, something's gone wrong with this process. The tag can't correctly decrypt the information that's come to it. Therefore, it would be stupid to send back an encrypted response. So it has to be unencrypted. Well, we've now got a canary that we can now use, or like an oracle, so we can now search for encrypted commands and know which ones are valid and which ones aren't, depending on whether we get this response or not. So what we'll do is we'll find one encrypted read page command. We'll then the encrypted version of that. We'll bit flip that to find the other 15 read page commands, which I'll come on to in a moment. And then we'll test each one to find out which one is read page 0. And from there, we'll recover key stream, and using that key stream, we'll attack the tag and read all its data. So the naive approach would be to cycle through all 1,024 possibilities, and for each one, initialize the tag to that same position, that same key stream, and send the next one in our sequence. And each time we get the error response, go around the loop, reinitialize the tag, send the next one. And eventually you'll get a response that isn't the error, and therefore you know you've got a valid read command, and then you can then use that to try and find the actual read page 0. But that's naive. We don't need to be quite as brutal as that. An encrypted command the second bit has to decrypt to 1, because for read page and read page inverted, the second bit is always a 1. Because we have the 5 bits followed by the inverted 5 bits, we know that the 7th bit must decrypt to the inverse of the second bit. So it must decrypt to a 0. Equally, the 6th bit decrypts to the inverse of the first bit. The 8th bit decrypts to the inverse of the 3rd bit, and so on. So not knowing the key stream and not knowing which command we're trying to guess, what we can do is we can actually hold the 4 bits in the right-hand side, J, L, M, and N, as zeros and not care what they decrypt to, and then enumerate E, G, H, and I to try and find something that will decrypt to the inverse of whatever they decrypt to. So we're only brute forcing those 4 bits to find that bit. But we also need to brute force F, because it has to decrypt to a 1, and K, because it has to decrypt to a 0. So we only end up with 6 bits we actually have to brute force, which gives us 64 possibilities, 32 on average, before we get a hit, which is half the amount of transactions. So we've halved the amount of work. Seems a bit daft, but You save where you can. So we go through that process and we find one encrypted command. We assume that that encrypted command we found is EFGHI, JK, LM, and N, each of those representing an encrypted bit. Now, if we'd had this particular key stream and we had that particular encrypted command, we wouldn't know the key stream at this point. Imagine that decrypts to read page 4 inverted, and then the second half is the binary inverse of that. Well, we could flip the first bit and turn it into a read command rather than a read inverted command. But we'd also have to flip the 6th bit to maintain the integrity. Because it's a stream cipher and it's malleable, because there's no integrity check-in beyond this nonsense they've built on top, we can flip bits in the encrypted version, and that will flip the same bits in the plain text version after it's been decrypted. It's a good reason not to use stream ciphers. So if that was read, if we originally have a read command, we could flip that bit and get to a read inverted. And if we originally had a read inverted command, we could flip that bit and get to a read. But if we flip the first bit, we also have to flip the 6th bit in order to maintain the integrity. Equally, we could flip a page bit. So if we were looking at page 4 originally, and we flip the 5th bit, that would turn it into page 5. Equally, if it was page 5, it would go to page 4. But at the same time, we have to flip the last bit, the same bit in the equivalent on the right-hand side, in order to maintain the integrity, so that when it gets decrypted, the second half ends up still being the binary inverse of the first half. Because of that, we can generate a table of all 16 possible commands from the one that we found. So we can do we do on average 32 transactions with the tag to find one read command, and then we can just, in maths, just bit flip that until we get the other 15, which takes no time and no RF communication to do so. And as you can see, that's just a binary process of walking through. It's just every bit we flip on the left side, we also have to flip on the right side, and we don't flip K or F because we know they already decrypt to the right values. So we now want to find the read page 0 command. We've got 16 possible encrypted commands. Obviously, each of these has been encrypted with the same key stream because we always initialize the tag to the same point, so it generates the same key stream. So what we'll do is basically cycle through the 16, initialize the tag, send the encrypted command, test what we get back, and if we're getting back the right kind of responses, we'll then use that to recover the key stream and attack the pages. So we'll carry on with our emulated reader, which will generate the same key stream every time we initialize it. And the way we're going to do this test is this. We're going to assume our guess is correct. And if our guess is correct, then it will decrypt to the read page 0 command, which we know the binary pattern for from the standard. And if we're right, the 32-bit response we get back will decrypt to the UID, which is in page 0, which we know because it's in clear at the beginning of the protocol. So we can XOR that, and that will give us the first 42 bits of key stream, right? But we don't know if we're right at this point. So what we can do is we can use the extended version of the read page command to generate a 40-bit version of the read page 0 command, which is essentially read page 0 repeated 4 times. As you can see, it's just the same binary pattern 4 times over. So when that gets decrypted, it will be able to check every block of 5 is the inverse of the next block of 5 all the way along. And what we do is we take our the first 40 bits of the key stream we think we've recovered, XOR that with the 40-bit command that we want to send to encrypt it, reinitialize the tag back to the same point, so it's using the same key stream, and send that 40-bit command, encrypted command. And we'll either get the error response, or we'll get back a 32-bit encrypted value. If it's the error response, it means that when it decrypted that, it didn't pass the integrity check, which means our key stream is incorrect, so our guess is incorrect. So we go around and try the next guess. But eventually we'll get a response which isn't the error, and therefore is the encryption of page 0, which is the UID, which we can then XOR to give us the next 32 bits of key stream following the 40 bits that we've recovered. And we now have 72 bits of key stream based on a replayable nonce using the length extension vulnerability within the tag. And what we can do with 72 bits of key stream is we can initialize the tag and use it to encrypt a read page command and use it to decrypt the response that comes back, and therefore cycle through and read every page. So there's 8 pages to read. We can ask it systematically, one after another, to read each page, reinitializing the tag each time for each page that we want to read, so that we're always using that same 72 bits of key stream. So I implemented this using a tool called rFiddler, made by Aperture Labs, Adam Laurie and Zach Franken. It only works at 125 kilohertz, but it's much better than a Proxmark for low frequency RFID. For high frequency RFID, 13.56 megs, use the Proxmark, which Adam Laurie wrote the software for and typically works quite well. But for low frequency, I say the rFiddler is a much better tool. It's all open source software and hardware. So you can theoretically build your own, but you can certainly get the software. So on their GitHub, which is Aperture Labs Limited, you can not only download all of the firmware, like you'd expect, but they have a page which explains how to set up the IDE. So you can load it all into an IDE, and then you can start modifying it. And when you look at it, it's probably a bit small for you to see. It's basically C, and the code's reasonably well commented. So you can kind of go through and make your own functions, which is kind of what I did, in order to implement that attack. And again, it's probably a bit hard to see, but when you need a low-level radio read and write kind of command, yes, transmit and receive command, which is something I don't know a lot about. I mean, I knew very little about RFID before I did this. I only got interested in this because of the crypto, but now I need radio functions. I simply hunt through the rest of the code base to find where Adam's done a transmit and receive, and steal that function call with those parameters and insert that into my code. And that works. So most of what you need is already elsewhere in that firmware. You just need to find it and then put it into your own functions. So as a result, I've added a number of extra commands to the rFiddler. So sniff PWM, which sniffs pulse width modulation traffic coming from a reader, already existed, but with no parameters. And I've added parameters to clear, store, and list the traffic that it records. And it's specifically looking for encrypted nonces and challenge response values. HiTag2 crack will implement crack attack 1. Attack 2, from the paper, needs 2048 bits of key stream. So using that same approach that got us 72 bits of key stream, we can repeat that over and over and over again and extend it by 30 bits at a time until we've got 2048 bits of key stream, which is what HiTag2 key stream will do. And then we can use that to attack the cipher in a different way, which I won't necessarily go into. HiTag2 reader, once you know the key, you can use that to read any HiTag2 tag from that system. And if you use the S to store, it will store them into NVRAM. So you can actually power the rFiddler from a USB battery and then just go around and steal people's tags without having to carry a laptop around with you. And so those last few commands clear the memory, count how many things are in memory, that sort of thing. The way the attack works is we go into HiTag2 mode, we clear the PWM storage, we would stick it in auto-run mode so we could power it from a battery. We'd stick it on the reader, provide the tag, that captures the value we need, plug it back into the laptop, and retrieve those commands and then use that to attack the tag, which is what we shall do now. So, live demo, because what other kind of demo is there? Right, I just need to, so I've got two rFiddlers here. One of them is going to pretend to be a reader, this one here, and this one's going to be our eavesdropper, which is going to be on this screen here. Should be that one. Right. Can you see that? Yeah? Good. Right, we're already in HiTag2 mode, but we would do set tag HiTag2. I might as well do it anyway. In fact, maybe what I'll do is pull that up a little bit so that people can probably see that a bit clearer, maybe. Ooh, well. Something's going wrong. Might be coming back. It's back. That bodes really well for a live demo with radio, doesn't it? Okay, let's hope that it doesn't matter. 10 minutes, yeah, that's good. So we are going to sniff PWM clear. So we'll clear the memory. I'll just hit list. There are no PWM traffic stored. So we'll now put it into store mode. Right, and you can see the reader's start auth command is being transmitted. I'll get my tag, and if I can get that onto there, in the right place, we will start to see, oh, there we go. So that's capturing, that's the reader talking to the tag and sending the encrypted nonce and trans response value. And the sniffer is recording those. Obviously, sometimes it's failing, but that's partly to do with this setup and other radio things that are going on at the same time. So if I then list that out, we've got a whole load of nonces and trans response values. I will stop the reader because that always messes with it. Now, all we're going to do now is move the reader out of the way, place the tag on the R-Fiddler coil. If we do UID, no, we just need to move it until we can get. Shame, am I on the right one? Yes, should be. Okay, so we now got a UID of the tag, right? So we're talking to the tag. We can now run HiTag2 crack, and we provide it with one of these pairs. So we'll just take that one there, for example. And it's now going to find a valid read command, and then once it's found one, it's going to determine the read page over command, and then it's correct the tag. So it's as fast as that. They are the 8 pages of this tag. If you care, pages 5 and 6 contain my office phone number. So pages 1 and 2 is the key, page 3 is the tag password, and then just random values in there. And once you have the key, so we now have the key, we could put this into HiTag2 reader mode, and we could copy in the key, which will be that half of that page there, followed by that page there. And now we could just read the tag like that. But equally, other tags from the same system, we could read, and we don't need to crack these because we already have the key. We can just read them straight out. So at this point, we could just bump into somebody else who's got a tag hanging around their neck, and in a split second capture the details from their tag. Which means we can now compromise the entire system and clone people's badges. The way you then clone would be to copy this information to a virtual tag, put a new HiTag2 blank on the thing, and write them to the HiTag2 blank, which the R-Fiddler can do. So, I say tag cloning, very straightforward. The UID you can't change, but it's not a problem because it's only used to randomize the RNG as part of the authentication. They don't make access control decisions based on the UID. I'll make the closing remarks, and if we've got a moment, I'll show you attack 4, possibly. So it's a really good attack, and as you can see, it's really quick, but you do need a valid tag. So you need to steal a tag, be a contractor, be a visitor, whatever, to get a tag to attack. If the tag has been configured with pages set to write-only mode, or not even, but not readable mode, then you wouldn't be able to read those tags. In fact, if I can demonstrate that. Oops, no, sorry. Sorry, this is 5806 followed by that. So I've got another tag here which is read protected. So if I put that on there, oh, sorry, I'm in the wrong window. That's why. I can see it. Right. So if I put that on there, it should Right, so that one, you can see pages 1 and 2 are coming up as X's because they're set so they're not readable. So even though you know the key stream, you can't read the key, which obviously defeats this attack and is quite annoying. Well, all the other attacks in the suite will attack different parts of the system just to recover the key. So attack 2 will recover PRNG states from the key stream that it generated and roll back to recover the key from the initialization phase. Attack 3 takes 136 nonce and challenge response pairs and exploits a bias in the tap positioning in order to work out what the key is. Attack 4 takes 16 to 32 nonce and challenge response pairs and exploits a probabilistic attack to do with correlations between PRNG output and the information that we feed in. Attack 5 is the GPU brute force. Attack 6 is the GPU brute force but done distributed. Attack 7 is the x86 new optimized brute force, and attack 8 is the GPU optimized brute force. So they all attack the key and recover the key. That's kind of saying what I've just said. And how long they take. So the best attack to date was 15 minutes, and now as of this year, you can do it in 40 minutes on a CPU or 1 minute on Amazon or on a GTX 1080, which is quite nice. The point of the talk is to say that I think there's a lot of interesting gems in the world of cryptography in the academic world, and I think as hackers we often miss that, and I think there's probably a lot more to mine. Because they don't generally release their tools, we don't generally notice it as hackers or pen testers. And if we do go and mine their resources, I think we can find a lot more interesting stuff. And I think we should be implementing those things because I think there's a lot more to find. So that is me, other than the final demo, if you want to see it. Thank you.
Thank you, the Kev. Do we have questions? Questions. Perfect.
Hi. 2 questions. Is there any type of master key in the system?
No.
Okay. And the second question would be, have you seen any implementation, like the real life living system out there, which doesn't use, for the authentication, uses only UIDs? Because that sort of misconfiguration is present in the MIFARE systems, that even there is a security sort of built in, the implementation is just abandoning them and just using UIDs for...
Yeah, you do see that, but because HiTag2 tags are more expensive, they generally would just use EM4102s for the same purpose. But you do see HiTag2 in hybrid mode, where they use the public data that gets broadcast as an authenticator, which is public, and then you can use that. So you do see that, but this is sort of specifically breaking those systems that don't. So.
Can you think about any secure implementation?
No.
Well, thank you. Very, very interesting talk. It was great. Probably a very naive question on my part, and the answer might simply be go read the paper. But, I guess you've boiled down this very complicated academic paper, but it didn't seem that amazingly difficult. Like, what did they do in the paper? Did they wrap it up in abstract algebra and rings and really complicated stuff? Or?
Yeah, they didn't use like block diagrams the way I describe it. I mean, one of my skills I think I have is taking complicated things and turning it into something that we could all understand, because I like to see things in simplistic format. They're basically describing that all in maths.
Like abstract algebra, rings.
Kind of thing, yeah.
I see.
And
So could one of us, a non-academic mathematician, read their paper?
Yeah, you can. It's just that in the 5 years between the paper and when I started this work, no one on our side of the fence You know, people were requesting implementations on the RFiddler forums and the Proxmark forums, and no one came forward. So people were reading the paper but not implementing it themselves, not knowing how to, I guess. So yeah, I think with effort we could all do this. It's just it takes effort to get through that barrier. So.
Okay, I was a bit lost about the length of the communication you need with the reader, like the measured in seconds, and the length of the communication, measured in seconds again, with the card you want to copy. So the practical attack takes how long time?
Yes, so you need to capture communication between the tag and the reader. That takes a split second with an RFiddler. You then need to attack the tag, which takes about 30 seconds to recover the key. And from there, you can use the key to read any other tag in a split second, to put it into context. The thing with this one is you need a valid tag, because you need a tag that the reader can communicate with, and then you're going to attack the tag and recover the key from the tag, which is why it needs to be valid. In all of the other attacks, you're attacking the reader infrastructure. You just need a tag that the reader will talk to and give you encrypted nonces and challenge response values for a particular UID. So you can theoretically use a blank just to capture those values. The only situation where that doesn't work is cars, where they whitelist the UID to the car key. So you have to have the right UID. Or on hybrid systems, which expect certain public data before and after the communication. So you need to then go through an extra step of recovering the public data off someone's tag, which you can just read by bumping into them. Program a tag up with that information, and then use that blank, well, that semi-blank, to go and recover nonces, which you can then use to attack the key. I know it sounds really complicated. When I did this at 44Con, I had 2 hours, and we went through 3 attacks. Like, if I was to go through all of them, it'd take forever.
So since we have a coffee break now, I think I can say thank you, Kevin, and further questions can be asked in the coffee break.
Thank you.